Hey.
It's like, I'm sorry, that's 15 problems.
I remember whenever I was in my second semester, and I'm
cool.
like, I have to really be devoted to this grading and like.
Tomorrow is the last day to submit that.
Now I'm just like,
to finish last.
just everybody gets A's.
Yeah.
Grading.
Yeah. Fish to fry.
I have next Tuesday until I have up to Tuesday. One student came in my PLC session and solved all this homework. Now I'm grading. What I
Just be like, this is good.
yeah. 100 out of 100.
That's so funny.
Yeah.
When I took over, well, didn't
Even
take over, when I was
remember his coffee.
when I was assigned to help Ty last semester, it was right after we did that angular momentum thing, and I was like, God, I'm glad I'm not grading this lab. And then I got put in grading that lab, and the first one I had to grade was the angular momentum. I was like, no!
It really backfired. I'm in that lab now. I haven't even started grading it. It's me and Hanshaka who just got here. So he's asked me like, how do you grade this online lab? And I'm like, I haven't done it before, but I'm just gonna give everybody A's. Like,
I find the student and take their pulse. Yes.
I mean, I just, I already have, like, this optics lab, even without the grading, like, there's just 7 hours of class meeting times that I have to be at. That's without grading the presentations. So it's like, if Chandra, you're still in the class, I mean, I want you to be able to stay in it. But if you do drop it, then hopefully the 3 students will be in one group.
Yeah.
You know?
So you have 7 hours of meeting time for a lab that's 1 hour?
There's 4 students, right? So we meet on
There's
Thursday.
4 hours of meeting than there are students.
Literally. We meet on Thursday
I will
for 2
decrease
hours.
your duty time.
What?
Duty time, I will reduce your duty time.
Yeah, but I want you to be able to stay in it if you want. I mean, I totally understand.
You got
So,
your paper, right?
but
From the
I'm willing to work with you. So whatever you decide, we'll make it work.
I did, thank you.
But yeah, on Thursday, it's the 2 hours the students do the presentation. And then after that,
When you
I
said
have
that,
an
I
hour
thought
before
there
the
was a homework
601
day. I was like,
study.
But there is a
Then
homework
next
now.
Friday,
Okay,
that's
that's
the
homework.
first group
that's
of
fine.
2 hours. And then an hour break for SBS, because all of the students are SBS. And then another 2 hours. 4 hours Friday, 3 hours Thursday, and then I grade the presentations. So I'm like, I'm actually really interested in learning about this stuff because I've never taken an optics class. But like, where do I draw that line?
the best way to learn is by teaching it. On the spot.
The best answer to give is, I don't know.
I don't know, but let's find out together.
Yeah, right. That's okay.
There's so many, like, just, is this okay things that happen around?
Yeah.
Like, is this allowed?
But yeah, that's why my 223, like, my focus, my priorities on 223 have diminished significantly.
Oh, yours is too? I was just sitting in a chair spinning around talking about how like easy this lab was going to be.
Now that you have 100 students for 298.
Yeah.
Whenever I was TAing for him last semester for the 299 with the 50 students, he was like, Zane, for your sake, I really hope you don't get this section because it's gonna be so hard. We always have the 200 students for 298, and I'm like, oh
Yes.
wow, that's very generous.
First homework.
Thank you.
hope today when we finish, you can
Who
start
says
to do
thank
that.
you for homework?
Yeah.
Do you have more?
Yeah, he'd like another 3
Thank you
problems,
for
please.
just 1, 2, 3 questions.
I'm grateful that it's only one-sided.
Okay, but each one.
Do you remember the
The
midterm
third one
last
takes
semester?
time. Now you are second quantum, so you are asked to do more complicated system of problems. Okay, now let's continue. We start with the spherical potential wheel. Just remind you. Then we discuss two cases: energy negative or energy positive. Regions, region 1 and region 2. So, also we can mark energy positive or energy negative. So we know if energy negative is here, right? Energy negative, then we know the particle bounded within the wheel, and we have the discrete energy numbers. If energy is positive, we know that like particle has a certain kinetic energy and come here, influenced by the potential wheel and go up. So today we are going to discuss these two cases. First, the radio equation, right? So equation. We have a two, so I just try to remind you. We have one is within the region 1. I give this R1. Second one, region 2, same thing. Here we do not have V naught, so we will have 2 n Okay. As I mentioned, there are two cases depending on the initial energy is positive negative. So now let's discuss the first case. Energy negative. Bounding states, right? Case 1. So that's bounded. Okay. For this case, I think we end up last class. We have the formula of the equation, the radial equation rewrite. Since here this is negative, so we use the absolute value, then we have a negative sign. We will have the equation, the radial equation is here. 1 minus square. Partial R, square partial R1. The first term, they keep saying the second one plus. Okay. Here, 2m over h bar square. Now inside here, this is a minus absolute value e, and this must be here. 0. And the second one. This one we have minus 2m over h bar square. This is absolute value e. And here is a minus again, right? So it's L plus 1 over r squared and r2. Okay. This is for energy negative, so we have we use absolute value, so we have taken account this negative side here. All right. Now let's solve. Okay. First one. Let's consider region 1. Region 1 is this equation, right? So region 1 here we define makes the equation easier to see this behavior. So we define Ki square is 2n over h bar square minus absolute value e plus v naught, which is definitely positive since we know the energy is negative, so the absolute value energy is smaller than the absolute value v naught, right? So we have to introduce k squared, definitely it is positive. So we introduce this, and then the equation here, this one, I'm going to quickly just jump the intermediate step. So now partial r squared, partial r, I, partial r. The first term here, 1 over r squared, I multiply both sides. So even here you have r squared here and r squared here disappear, right? So, sorry. Oh, okay. Yes. Let's do that again. And I have to know this one. For free particle, so there's another most step. And first here, so that is k I squared minus L plus 1 squared. Right? Then we do this derivative partial r squared with one term, another term. So we have a second order partial derivative for the r1. Then this one is reduced to r squared. Then I multiply the r squared here. So now r squared partial second order partial derivative r1 partial squared plus 2r. How to get it similar as we do this for the free particle. So I just jump that one and plus. Now we have a k I squared r squared minus L plus 1. What you did is just do the detail inside and then just multiply r squared. So inside we have this term here and the second order, and then another one is 2r, right? So this term. And this one, when you do that, we have r squared here. Right? Remember this. So this one, we mirror that is a spherical Bessel differential equation. So we immediately got the solution. Right? This is a spherical the solution R1, which is the region 1. Okay, here. Since now we take this as variable, remember? So this is our argument here, right? This R1 as a function of K1, KIR, that be the spherical Bessel function. If you remember, we discussed. There must be another spherical Newman function, but we know for r go to 0, that function that diverge, right? So the physically accept is this one. This is we already discussed in the free particle, so I just immediately write down this. Remember? Okay. So that is very quickly we got the solution for this one, right? In region 1. Now, this is why when you're familiar with a spherical, a special differential equation, you know the solution and you know the behavior of solution, so you can quickly write down the solution. That is a region 1. Now we go to region 2. For region 2, we also define here, we have another term, so we define another KE equal is 2m h bar square up to right? Then it is positive. So if we define, then this equation also reduced to 1 over square partial r square partial r2 partial r. And plus, now here we have a minus sign. So the minus sign, I'm going to say that is I squared, right? So here, inside is I K E R square minus L plus 1. So that is, the I come from where? From here we observe this negative sign. So now the argument is I K E R in the region 2. In region 1 is K E, I K E R. In the region 1 is K I R.
In definition of K, it is square root.
Okay. Okay. So now this solution, again, we can rewrite from here to here, same thing. So we will have, you will see you have this second order partial derivative of R2, R partial square, and plus 2R partial R, and then plus. Okay, sorry, this one is, I jumped too quick. So this one is, it's not here. There's no R square. Right? That is like this. And then now down to here is this one. I K E R square minus L plus 1. And again, this one, you compare both, they are all is spherical Bessel differential equation. The only difference, this one, the argument is KIR. This one argument is IKER. You may say, oh, here, yeah, we can observe that as a, let's see. I think there's, yeah. If you remember, I multiply IKE here, right? So that is become IKE. You can multiply IKE square, so that is the argument of this one, right? Okay, so the solution. In this area, the solution are 2R. If you remember, for the spherical Bessel function, it converges at the R go to 0, but the Newman function, it divides it, and then R go to 0, but when R go to infinite, both are converge, right? So let's see, right? So now in general, we can write this in terms of this spherical Bessel function and plus minus I, the linear combination of this I K and R. Right, both are possible. Then we are going to discuss the acceptable function. So here, let's consider this one. It is because here we have argument I, so we need to be careful to deal with when R go to infinite. So now we are going to rewrite as, let me write down, in terms of linear combination of Hankel function. So, okay. So I think I have a B, L, or I think there's no R, so no R. I is here, it is not wrong. I is CL, and I is here. So now I'm going to BL plus, well, first kind of a Hankel function, and plus CL, second kind of Hankel function H minus. And here we introduce plus minus IKR is spherical Bessel function plus minus I in L I for this spherical function. So this is just rewrite in terms of this way, or you can rewrite this one is linear combination of spherical Bessel function, spherical Newman function, or we just rewrite in terms of a spherical Hankel function. So spherical Hankel function defined as this, and then that's be also the linear combination of H plus or H minus, right? So that is depending on how you rewrite this linear combination. So now, the reason why we read that this way, then we are going to analyze when R go to infinite, which one acceptable physically, or which one is still finite, which one, or convert, which one is diverse, right? That is why we introduce this way can easily to help us to see. Okay. So, let's discuss or give you an example of this Hankel function examples to see the behavior of this. So first one, the plus minus when L equal to 0. So the lowest order, right? This is dependent on L. L is the angular momentum constant, right? So if L is 0, so we say 0 spherical Bessel function, or the argument is spherical Bessel function 0th order plus minus I n naught and E R, right? Then that we know this one is sine I k r over I k t r. That is the 0th order of spherical Bessel function plus minus I. This is a minus here. Minus cosine I k r over I k r. That is a spherical Newman function. Then this one, if I take minus plus outside, 1 over I k r outside. So here, take I outside. So here, I have a minus become plus minus minus here, and minus minus plus. So I take this one outside, then the inside is cosine I k r. The denominator is take outside, and then this one be. If this is a take this one, so we have a minus plus minus I, right? Take I is sine. Right? If I take I here, I have I, and the I is minus and minus plus this time. So then you can see this one is nothing but exponential minus plus I cancel, right? So I just I cancel 1 over k e r. This one is exponential I k e r. Right, so I minus, so this is a real. Exponential is a real term. K E R exponential minus plus K. Okay, that is zeroth order. Similarly, let's go to the first order, and then you will see the behavior of this. So that is H1 plus minus I K E R is J1 I K E R plus minus I N1 I K E R. And J1 is here. J1 inside. We have two terms. Sine I K E R over I K E R minus cosine I K E R over I K E R squared. Plus minus I and Strickland-Newman. No, this is a first minus cosine I K E R over I K E R squared and minus sine I K E R. So for the IKER square, we have a sine cosine here, right? We have a plus minus I here and minus I. For this first order IKER in denominator, we have another one. So you will see that is yeah, that is two terms. So I immediately write down the first term is plus minus I K E R square exponential I K E R. Similar as we deal with here, right? From here to here. And the second one is this first order is minus I K E R exponential I plus minus and then here 60 plus minus. Okay, and then you same thing. I give is a real, right? So finally, this I, okay, this is also I. This I cancelled. Oh, okay. This term we have a no I, right? So this no I. And then we have an I here, I multiply I both sides, so we have I. Sine is plus is I here. This one we cancel one I, so we still have I. So finally it's minus plus I over, sorry, there's no I here, K E R square. Take this outside, and then this plus I K E R exponential minus plus K. And some mistake. This square, so this one, is the same thing like this. I take this minus plus minus I here, and take this square. So here we have the cosine, this one, and sorry here. This is cosine here and sine. Sine we have I plus minus, so that is the exponential of this term. Then another one is this term, this one. So this both we have a minus. I take minus outside, so then the I plus minus I sine, right? Plus minus this one is here, this one. Does that make sense? Okay, and then this I square we cancel one, so we still have I here, but this is cancelled. This one multiply both sides, so the top and bottom, so this is minus 1 plus become plus. Limit of the line, right? So, okay. Then the same thing, so now let's look with R. For R go to infinite, since this is region 2. We are going to see if R go to infinite, is this the solutions are finite or diverse? If diverse, we can drop, right? So when you go to infinite, you can see the plus will go to finite. Or actually go to 0, since when, I think, just one. So that is finite, since it's negative. Go to infinite, this go to 0. But minus 1 go to the diverse. So the acceptable solution for R2 here, I rewrite in terms of this, so only this one, right? The accept one is EL. Now, EL, coefficient and H mass. The argument IK. Okay, so this is the two solutions. Now we have two solutions. I think I erase R1, right? This is just shown. Then we have these two. Now once we have solutions, the next job, we are going to determine energy. Since we know for this case, if energy is negative, and within the way also this bounded states, the bound states energy is discrete. Then how to determine this? Which condition we can use? The boundary condition, right? So the boundary condition gives us how to determine energy. We are going to use boundary condition to determine energy. All right, boundary condition, which we have only at this position, right? This R1 is equal to R2. So the boundary condition at R equal to A, we have R1, okay, L, you can use argument R since we use argument K and R, right? A is equal to the second function R2, right? That is the wave functions be equal at the condition since this be continue at the boundary, and also the derivative, the first order derivative. Then R equal to A is equal to the first order derivative of second one, and KEA, that's KR, so this R. So we have two equations. These two equations can help us to determine the allowed energy. Now, for this case, we usually combine these two equations into one because this can help us to simplify the condition equation. So now let's use the equation 2, equation 1 divided by equation 2. So here we have left hand side is equation 1 is R1, right? KR, KRA, and equal to 1 over R2 by KEA, R2 ER, KEA. Now I'm going to say equation 3. So that means we combine equation 1 and equation 2 into equation 3. There's only one equation, Then the remaining is we are going to do substitute R1, derivative R1 with respect to R, and R2 and derivative R2 into this equation. Okay, so now let's left hand side. Left hand side is I already write down here, right? It's R1, R2 here. So left hand side, just immediately write down here. That is 1 over A L J L K I A, right? That is this one, R1 K I A, and D J A L here, J L K I R R. Now I'm going to rewrite like this. I still keep R1, sorry, J. First, this one cancel, right? This coefficient, so that's the one. Then second one, I keep here. This one still keep here. Square Basel function. And A. Now this one, I'm going to. This is the variable is KIR. This is a R, right? So I'm going to multiply KI. Then this becomes a D, KIR, D, GL, KIR, and A. So here I have the numerator KI here because I multiply this. And the right hand side do the similar things. Right hand side is a spherical Hankel function, the first kind. So that is 1 over BL H plus L I K E R, sorry, K E A, this A, and then there's a B L B H plus L I K E R B R I to A is equal to same thing. B L cancel, so I have a denominator K H plus L I K E R, I K E A. Then I also, now I multiplied IKE, so I have a IKE D H plus L IKE R D IKE R IKE. This is both sides. I replace the R1, R2 by its solution. Okay. Then this left-hand side should be equal to the right-hand side. Then you can see here, we have, let's see, yeah, I just keep it. So that is a K, here, Ki, right? And denominator is J, L, K, I, A, E, J, L, K, I, R, E, K, I, R, I, A equal to I, K, E, H plus L, I, K, E. This is finally we obtain the condition or boundary condition, and we are going to solve this one to find a solution. But this really depends on L, right? Depends on L. So different L, we will have different solution because different L, the H L plus and the J L is different. So that makes make the things complicated. Now we just show one example when L equal to 0. Then you know how to do that. Then you can do the L equal to 1 or higher. Okay. So now let's do that. See what kind of equation we can get from here. So L equal to 0 case. Okay. Then we have first, if you let's just give you the information here. J0 KIA is sine KIA over KIA. And the dj0 original KIR dKIR IA. I gave you just do this and you will see this is a cosine KIA over KIA. We do the derivative for first for sine and then to the denominator minus sine KIA squared. Okay, that is for the left hand side, which we are going to substitute here, right? This part. Now the right hand side, if we know each individual, then we can just substitute this into. So now let's give you h plus naught IKEA, which is minus 1 over KEA. If you remember, I just remember here, right? That's what I release here. So that is exponent minus KEA. That is derivative. Equal to, just get your final IKEA exponential minus KEA and plus I over KEA square exponential minus KEA. Okay, so when we have these two pair, one is for the left hand side, the R1 region, another is for the right hand side, the R2 region. Then we are going to substitute into that equation. Let me give you okay, so the left hand side, let me just do one more time. Left hand side, 1 over J naught KIA E J naught KIR is this term. This term divided by this. Let me give you an example. I think you can very easily just do the division. Divide cotangent. Here I minus 1 over right, you substitute it into here, and you will see this term cancelled, but only the remaining this one. And this term will have cosine side to be right? So that is right hand side 1 over h plus naught IKEA EH plus naught IKER final is I minus 1 over IKEA. Yeah. Okay, yes. I do not, I think I have this one, not right hand side, but let's do this way. Just this term. But I have also this one. Now we substitute this into here, but we have the left hand side, we have KI, right hand side, have IKE, right? So they multiply this. Now finally we have the equation. So now the left hand side is the cotangent, this one, right? So we have KI, right? KI. Multiply this, and this inside cotangent KIA minus 1 over KIA equal to right hand side we have IKE multiplied this. So IKE, and this one is I minus 1 over IKE. Simple, right? After we do this each term substitute. Now here you can see this one, if I multiply, let's see, K. Actually, you can see here, this one, if you multiply here, it's 108, right? And this one here also 108, so they cancel, right? This term here is minus 108. This term here also minus 108, so they cancel, right, both sides. So only these two terms. So finally, you have a K I cotangent KIA equal to this one. I is minus K E. That is final equation. And this is a transcendental equation. So finally, you can see if for the zeroth order, at least we find this is the solution or the equation to find the determinant E. Now, how to determine this one? If you remember it in the one dimension chapter 4, we also deal with this kind of this equation, and we try to use graphic to help us to find the solution, right? So in order to do that, then I'm going to multiply A. Let's define. To make this graphically to help us to make the solution, look at two curves, both sides, left-hand side curve and right-hand curve, they have an intersection, so that is solution, right? So let's define alpha is KIA. And so the alpha squared is KI squared A squared. And remember KI is 2m h bar squared, take K squared, and absolute value E minus minus remember that is we introduce another parameter alpha. So once we solve alpha, we know Ki. When we know Ki, we know the energy. Right? So that is and then beta is Ke. Okay, so beta square is Ke square A square, and remember Ke is this term, right? So then you can see if we introduce alpha beta, then the alpha square plus beta square is these two terms together, and then minus is minus. This is a this is a minus. This is plus, right? Remember we have energy negative, we get this one. So this one is positive. Okay, that is actually right. Then if I add together, this cancels only this term. That is A squared. A squared 2m h bar squared or multiplied absolute value gamma squared. Then you can see the relation between alpha gamma, beta gamma. This is like a spherical or the radial. Alpha plus beta always equal to gamma, right? So gamma you can see here. Sorry. It's this one, V naught. So gamma is a function of V naught. So given V naught, how deep it is, how deep it is, and how the widows of wheel, that will change this one. And once the V naught and A given, this one's fixed. If this fixed, so this alpha beta change, and alpha beta give information about the energy, and that follows a kind of a spherical, right? So now let's rewrite. If we introduce alpha beta gamma, we can rewrite the transcendental equation in terms of alpha beta. So this one, I multiply A both sides, right? Then this is alpha minus beta, right? So finally you will have the translation. This one go to minus alpha cotangent alpha equal to beta. Yes. So now that means left hand side always equal to right hand side. That solution it gives us a solution about the particular log value of energy. How to do that? That's graphically, we can analyze as a function of alpha. So that is okay. So that is a beta here, right? Beta is a function of. So here, the left-hand side is function alpha, minus alpha multiplied cotangent alpha. The right-hand side is another function alpha, which is square root of gamma square minus alpha square, which is a sphere. Now let's first plot the negative alpha cotangent alpha, 0, half pi, 3 half pi, 2 pi, right? And this alpha is angle, so we can go. And then, okay, pi, 2 pi, and this color. So you see this is negative. Your cotangent alpha is here, like this, right? But the negative is just above, so here. Which are defined on about the positive value is from half pi to pi, or from 3 half pi to 2 pi, right? So that is this negative alpha cotangent alpha. So second one, the right hand side is beta, which is sphere. So sphere is dependent on here, dependent on gamma, and gamma is governed by controlled by V naught and A, right? So that means we change, we increase V or deepen the well, we have a larger radius. Remember the gamma? Did I introduce gamma? Yeah, here, right? Gamma proportional to this V naught is going to the A. So that is beta equal to square root gamma square minus alpha square. This is gamma, not alpha. Okay. Then that's depend. If this V naught or gamma is small, there's no intersection. Then only we have enough gamma, we will have the interaction, right? So suppose here, forgiving we have this is alpha, since L, I select L to 0, so alpha depends on L because this is equation, right? So alpha 0 but n. How many points? In this case, this is, I'm going to say this is alpha 1, right? Only 1 point. There's only one states allowed. If enough deep, right? If it's too small, there's no. Then when we increase, this one still 1. This is alpha prime 1, not because it's dependent on another V naught. And then we go to enough, so now alpha double prime 1, no, and this one is alpha double prime 2, no, right? With larger enough V naught, we can have a 2 solution, or you increase maybe 3 or more. But how many solutions, it depends on the V naught here, right? How much is the gamma? But you can see it, yes, it is discrete. And this, how many allowed this energy or states depend on the potential wave and the radius of the potential wave, how deep and how many. So in general, we will have solution, the alpha square alpha here, right? Alpha square is, suppose we got this intersection, so that satisfies this, but this is a k I square a square, that is give us here, this one, right? A square minus 2m h bar square. Now correspond to this one, I'm going to use E n. But here, I use this 0 because it corresponds to L equal to 0 case. You can have the solution and this one plus O n H bar square V naught. So by solve this, we will have a lot energy is you move to the right hand side, that is to the right hand side. You will have a V naught minus H bar square O n square alpha. That is how to obtain this a lot energy. Okay.
Sorry, I'm a little confused with the alphas and the primes and how you're labeling things. There.
Okay. So I label this one double prime over 1, and this one is dependent on this value.
Okay.
This value, because this value given only have only one circle, right?
Right.
If you increase another circle. So for one circle, for this circle, there's no alpha, no intersection. But given some particular V naught, I have, in this case, I have only 1.
Right.
So I just use 1. But when we have increased V naught another circle, now still have, yes, actually, yeah, I'm going to, yeah, still here, but it's a different V naught. So I use prime. Then but it's still first one because it's still in the range between half and pi.
Okay.
The first interaction between this first curve with the circle. But then if the V naught is bigger enough, I have 2 points. Then the first point still in between half pi and pi, and here I'm going to use alpha double prime 1, since this one is correspond to another V naught.
So like your alpha double prime 1 is your first intersection of
the bigger V naught, yes.
Okay.
Yeah. So actually alpha, in this case, n is a function of V naught A. Yeah. Actually it's functional now. But given this, we will have one side of alpha, one side. But if this change another side, so that the side here is really dependent on this one, and this one, this one. Because this is given gamma, then we will how big the circle is. Now, how about the L equal to 1? Please, I want you to do that. Try to follow the same thing, but the translator equation may be a little complicated since you need to find what is J1 and the D give for J1 and the H plus 1 and the D give for H plus 1. But the procedure follows the same. Then you can discuss whether the solution looks like. If it is, you can do it graphically, can help you to analyze the solution. All right. Now, this is a case negative. Now we go to positive. Because positive physically is very also important. So let's consider a case. All right. Remind you, so we have the equation video. Equation partial R squared partial R. And here, now since energy is positive, so I do not have an absolute energy. That is only simply energy plus the potential and small and plus. That is different. Different from this negative. That is region 1, and region 2 also energy is positive. So now we still do this define 2k, right? Now here ki square is a 2n h bar square e plus v naught, and the ke square is 2n h bar square over e. Then you just sub the equation, I just, partial r, r squared partial r, plus square minus L and plus 1 square r1 to 0, region 1, region 2, partial r2, partial r, plus 3 square minus L. Here we do not have I, since the energy is positive. That is different. And that's different, you will see the solution different. Can I erase this one? Okay, I just immediately got the solution since you already familiar with this. Solution for the R1, R. You already changed the argument since that spherical Bessel function. Again, in this small when r go to 0, the Newman function diverges, so only the acceptable is spherical Bessel function. Okay, that is 6. And for this R2, in this case, since here we do not have I, and you will see the Newman spherical Bessel function, spherical Newman function are all finite. That's like sinusoidal function. So you have to select both. BL, spherical Bessel function, plus CL, spherical Newman function. They are all allowed. That is different. So we have to take into account this. Now in this case, we want to rewrite the formula such that we can analyze this behavior easily. Now let's do this. This one I'm going to take multiply the square root of BL square plus CL square, and inside BL divided by BL square. That is manipulate. We want to do this, and you will see if we do this one, plus CL BL square plus CL square. When we do this, you can see here, this one is a ratio less than 1, right? This one, this is like a sine cosine, since you see, if this term square plus this term is 1. So that is a kind of sine cosine. So now I'm going to say this is a BL, and define the square root of BL square plus CL. It's another constant, and the inside is JL. AR multiply, I'm going to introduce cosine delta L plus NL equal Newman and sine delta L. Since here DL we introduce is BL square plus CL square, then the cosine delta L is simply the BL square BL square plus CL square, right? And sine L, CL, that is way. And when you interpret it this way, you will see this is a very simple kind of phase change, right? Or phase shift. So that means this, let's see, the reason why we write this, and the delta L is the ratio of tangent ratio of CL to BL. This is we do not know. This is unknown. Okay. If unknown, so now we are going to solve this the delta L. How to solve this? Again, we use the boundary condition. That's since here we have also the boundary condition to determine delta L. Why you say why not energy but delta L? you will see here. First, we know that the potential, the energy is a lot higher than the potential wave. That is unbounded state, right? So energy should be continued. One-dimension problem we already discussed. So now let's use the boundary condition C. This is the unknown, right? So we are going to boundary condition again. We have used R1, then this R equal to A equal to R2, and ER I A. Do the same thing now. What we do is R1. This is a solution. We are this one and this one. The R2 we are going to use this one. Okay, so again, 2 divided by 1, you will have I just needed the substitute R1, R2 together, so now this have this Ki J L prime. Prime is derivative, right? So now I just use this. Right, it's a simple. There's the left hand side equal to right hand side is K E J L prime K E L cosine theta L plus N L prime K E A sine theta L and divided by J L K E N cosine theta L plus N L K E A sine. This is the transcendental equation here. And to solve this one, again, depend on equation. Here. Given L, we have a given type of the transcendental equation. We are going to deal with this again, start from L to 0, because that is a simple case. And then we will take L to 1 or higher, it's more complicated. So usually numerical is better than mailbox. You set up equation and write the code, you can solve graphically using numerical to find this cross section or intersection. So now again, let's see, please, L to 0, see that happen. In order to know that, we need to know the JL prime when L to 0 and NL prime to 0, right? So now let's first J naught K I A equal to sine K I A L. And we have both sides, right? This is JL for KIA, JL for KA. So different. The same thing but replaced by Ki by K. So that is then the first order duty is only for upper both. Okay, those are right both. Okay, then they are same, right? So now let's write down here cosine KIA over KIA minus sine KIA squared. And the G naught 1 of KEA. Same thing but replace K under KE. cosine sine then the n naught only have a ke, right? No ki, so we just take this one. Ke is minus cosine ke over ke. And n naught prime ke is sine ke over ke plus cosine ke squared. Okay. So what we need to do is substitute those terms into here. Then some terms cancel. Now finally I'm going to give you the final, since that is just an accident way to do it, right? So finally we have ki, substitute those into this transcendental equation, right? So substitute this one ki, that is T naught prime ki, T naught ki equal to ke, T naught prime cosine plus n naught prime sine L divided by k naught cosine L plus n naught sine. And then what you need to do is substitute those terms into here. So I give you final. Ki cotangent KRA equal to KE cotangent KE A minus delta. No, okay, this is also L equal to 0, so here is delta naught. This is a finally transcendental equation, and also looks like simple, easier for us to understand. How to solve this? Now, from this equation, you can see here we have a Ki, Ke, which is a function of energy and the V naught, right? Here unknown. So unknown. This one equation we have unknown variable energy and delta naught. One equation can have only definite one solution, right? If we have two unknowns, so what happens is the solution, these two will go to one of them is another function, right? So from this one, what we can have is we solve this one for two unknown. So what we have is one of them is another. They are not independent. Independent, they are dependent. So for given energy, we have Ke, Ki. Then you solve this one, you got the delta naught. And to change another one, you give another one. So delta naught is function energy. And we know the energy is continuous. In this case, is continuous. Not bounded in this case, right? So the goal is try to find the delta naught. How to do that? We are still use graphic to help us. Okay, we first introduce define before define. Here we define alpha is K A and beta is Ke A. So Ke here we already saw. I just so then this equation here it became is alpha cotangent alpha equal to beta cotangent beta minus delta naught. We are going to solve this. Both are cotangent functions, but one is a parameter alpha, another parameter beta. Remember beta, this is a KE remember KE square is 2me over h bar square, but Ki is 2me, 2m over h bar square plus e plus v naught. So this is bigger than this one, right? If this is bigger than this one, so in the graphically, the range, I'm going to use the function in terms of alpha. So the beta, if alpha from 0 to 2 half pi, then beta is already from larger than half pi, right? Okay, just let me remember this. So now, let me try to figure out. This is half pi. Okay, now let's look this term, this one. All are positive, right? So positive, we know this cotangent alpha diverges when alpha go to infinite and 0 go to here. So here we have, this is larger, right? So, okay, that's this half pi. Okay, that is this one. And the second one is here. Then how about this one? They are all cotangent, but as I said, if alpha half pi, then beta is smaller than this one, should be some pi half pi here. So the beta is something like right, so we have a translator at the intersection here. Because this decay ratio is different and the range is different, right? So that is, it is possible, even though the two cotangent, if the same thing, then there's no intersection, but if the different, in particular we have shift. So this also shift, this shift also try to make two curves parallel, but the shift, it makes some of possible to cross if the ratio is not same, right? So this is possible here because that is try to solve this one, then we can get shift. So the solution is try to find how much the phase shift can determine depend on initial energy This is initial energy, right? So depend on, okay, this one depend on both energy and also the V naught. So V naught, Ki, right? Alpha here. So that is this. The energy is positive. Okay, then we can discuss the physical meaning of this. Then I think we can finish this spherical visual graph. How to understand this physical meaning of delta L? Let's consider if and R go to infinite. If R go to infinite, we just look at R2, right? So we have R2. K-E-R and R go to infinite. It is this one. Remember that's DL, GL, K-E-R, cotangent delta L. Plus N-L, K-E-R, sine delta L, right? That is this original. Then when go to infinite, this one behavior has go to infinite, and this one go to infinite. So now I give you the result is D-L sine K-E-R minus L pi. L half pi divided by K-R, that is this one. and cosine W minus cosine KER pi KER sine. Let's follow this, and then I can keep on this. This is a general, right? So that's one. This is this one, and now this I keep here. So that is dl KER, and you can see this is a sine some angle multiplied cosine another angle, cosine angle. So that is a kind of sine KER. This angle plus this angle, right? Plus or minus, whatever. And this angle is a function of. Okay, so you can see this is sinusoidal function. For this case, we have potential wheel. Now let's remind for a free particle, no potential wheel. R is free particle when R goes to infinite. If you remember, because this one is a function of a spherical Bessa function which we determined last section. So this one is 1 over KER. And sines KER minus rho pi. So what's the difference? You can see this one we have a potential well, this one have free particle, but when the R goes to infinite, they are different, only the difference here, right? Difference, and which is a phase shift. So what's the difference is just a phase shift compared with a free particle. So this phase shift is due to that, due to the total effect of the potential difference, effect of I gave it homework number 3 is this case for 1 to 1. Okay, so looks like here. This is a scattering. Yes, actually the scattering is the scattering form. Okay, suppose we have a target here. We have a target, we have a potential wheel with A. So that is the potential, or target potential zone, right? That is the potential zone. And here we have an incident particle with initial energy and angular momentum L. So the particle initially, like plane wave, right? Particle go to this velocity. This is a plane wave. You have a glass, right? So I have to stop here. Yeah, okay. But I just repeat this part almost fine. We see this is a scattering chain, and that scattering is affected by the potential, and that is the effect is nothing but just change the shift, the phase shift. Okay, so homework number 3, as I said, that is for this case, but we take 0 to 1 and see if you can solve it. Okay, but again, I gave you a hint, right? So I hope Duncan can help you. Yes.
One for him.
Oh, okay, yes.
It's nice to have more people on the page.
Right?
What do you want?
Like, oh.
Fisher? Yes, for that.
Yeah.
I don't know why it sounds like through my headphones. Like maybe I just put my headphones in and everything's fine. I started playing with it. I changed it to this sound going to my headphones, but this microphone going from the computer.
Yeah.
And it worked. But I was in the PLC and there were other people, so I was like
Yeah.
trying not to have the sound through, you know. So
Whatever works.
whatever works. Hey, I'll see you all in like a minute.
Another class, right? Dr. Mendez, right?
Yes.
In the third floor?
Yeah.
Yeah, sorry, you have,
Oh, no,
I
that's fine.
forgot you have another class.
Prof, I think the clock is working,
No, it doesn't work.
so I think we have to change it.
Yeah, maybe next time I'm going to buy a new one.
Yeah, no, that's fine.
Buy a new one?
We will talk
Oh.
Yeah,
instead.
that is, yeah, I have always forgot this weekend, if I have time, when you guys see it. I want to replace that one.
Mhm.
Okay, see you then.
Thanks.
See you.
لا